Howdy, team. Share screen. Screen is shared. Awesome. So how did it go? Anything you want to ask me about your homework, for instance, before I show you something incredibly cool?
I have a question.
Sure.
Because I emailed you the project thing,
Yep.
do I still need to turn it in through my open math?
You do not. You do not. As long as I get it, I don't care. I really care how you get it to me. If it's through my open math or just emailing it to me directly. So no, yours is good. I responded last night, I think, to yours because I graded it before I crashed. So that was
Yeah, I
awesome.
saw that.
All right. So the good news today is you never have to learn how to take derivatives again. Like you now know. I mean, I say this a little tongue in cheek, but you now know everything you need to know about taking derivatives. Like just kind of like you left pre-calculus and it's like you now know algebra. You don't ever have to learn anything again. Well, you've realized in calculus that you don't know algebra maybe as well as you could have or should have. You just need practice now. But you were given the most ridiculous equations. I think there's one in your assignment that's something like y equals x to the 2x power or something like that. Whoever runs across an equation like that, we're taking derivatives of pretty crazy statements now. And so you need practice to be, good at that and so forth. But there's nothing else to teach you. It's not like we have to go on and now how do we take the derivative of this and what about the derivative of that? We're at the end of my note sheet. There's no more derivatives that we can take. You know them all now. That's kind of cool. What we jump to now for the rest of this term, actually starting today, is just how to apply this. Like, what can you do with it? That's great. You can take a derivative, but what can you do with it? And what I'm going to show you today is a really cool step in that direction. It's going to kind of tie, in a sense, everything we've learned together in such a way that maybe you start seeing, oh, I'm beginning now to understand how to speak the language of calculus. We've taken the derivative of everything under the sun, and now let's go use that skill, the skills that we have. It's kind of like the equivalent of you sat in this class and learned all these Spanish words, and now it's like, let's get on a plane and go to Madrid and like buy some coffee and go to an art museum and let's go do something with it. And that's kind of what's happening in calculus now. You have all these skills, and so let's go see if we can actually do something with it. So the first one in the last part of chapter 3, is called related rates. And I want to show you right now what I mean by that, by bringing something up that I've shown you before. So I'm going to go over to my other screen, share my other screen, and bring up the mountain shadow. So we did this project before where we saw that the rate that the shadow grew down here, let's see, is this in projector mode? No. The rate that shadow grew is kind of relative to where the sun is. And so let's put the sun really high in the sky. And now I'm just going to let the sun set. And down here, by the way, you can actually control how fast this plays. So I'm setting this at super slow. And now the sun is setting at a constant rate. Notice it's 55 feet. Now it's down to 50. The sun is setting. And what I want you to look here at the bottom is the shadow. Notice the shadow is not growing at all. It's almost like the shadow is not even moving. This dot is where the shadow is. Notice the point of tangency is moving. But you can see the sun is setting at a constant rate. It's just setting, setting, setting. Well, notice you can start to see the shadow grow now. The whole time the sun is setting at a constant rate. And now the shadow is beginning to grow, and you can really see it growing. Notice it's speeding up. Do you see that? The shadow is speeding up. And remember, this is me walking along the bank, and out here someplace I realize, my gosh, the shadow is going faster than I am. Notice it's speeding up. It's really starting to speed up now. Now it's really speeding up. Now it's flying. It's hauling. Whoa, it's going so fast. Wow, it's just racing across the screen. The rate that the sun is setting is related to the rate of the shadow, but notice it kind of depends where the sun is. If the sun is in here, notice the shadow is going super fast, but when the sun was up here, the shadow is hardly moving at all. It's just barely even changing. So when the sun is high, the rate of the shadow is hardly moving, no rate at all. When it's down here, the shadow is just flying. And as I mentioned, all of this entire problem came from just my own curiosity as a human being as I watched the shadow outrun me and I couldn't even keep up with it anymore. And I was like, what the heck is going on? Like, why does that happen? Well, we're going to completely answer that question today. And let's do that problem. Let's do that problem right now. Now, remember, you worked your tail off on that project just trying to figure out where the dumb point of tangency was, and it took like all the algebra and calculus you knew just to even figure out where the shadow even hit the mountain and nothing even moved. And so to figure out the speed of all of this stuff, man, it's like that must be really terrible. And so it is terrible actually if the mountain is a parabola, but I'm going to simplify this question a whole bunch. Revisit the shadow. So here's what I mean when I say I'm going to simplify this a whole bunch. Okay, so let's put the sun up in the sky right over here. There's the sun, and we're saying it's going to set. It's going to move down until it hits the ground. There's the ground. And instead of having a mountain cast the shadow, we're going to make this a little simpler on ourselves and just make a tree cast the shadow. So it's just a line. I'll even draw on a couple of branches on the top of it. So this won't be so hard. And so now, if you will, what's causing the shadow is just going to be the tip of the tree. And so based on where the sun is at right now, I guess you would say that the shadow is like right there, right? So this creates a little right triangle, that creates a little right triangle. And we're saying the sun is actually in motion. So it's going down. And of course, because it's going down, then this shadow right here is going to be growing too. Cool. Well, what do we know? Let's make up some stuff. And again, I'm trying to oversimplify this. So let's say that the tree is, I don't know, let's say the tree is 12 feet tall. Let's make it a fairly small tree. And let's say the sun is very unrealistically setting 16 feet away from the tree. In other words, the distance from where the sun is going to hit is over here. And again, I'm oversimplifying this a ton because the sun doesn't come down and land on the earth, right? That doesn't work so good. In a sense, a better model of what I'm really drawing here might be more like a car driving by. Have you noticed that? Like you see a car drive by at night, its lights are on, and it'll turn a corner and you see its shadow like go, or the lights go kind of flying across the trees, or you're walking along and there's a car behind you and you see your shadow on the ground, and as the car gets closer, the shadow kind of moves. And so you might want to think of the sun as more like a car driving by here just because of these tiny numbers I'm giving you. But does it make sense those two numbers are constant? Like the tree, at least for a few minutes here, the tree is 12 feet tall. It's not growing. It's staying the same for the short period of time I'm looking at it. And the tree is 16 feet away from where the sun is setting or where the car is driving down. But would you agree that the length of this shadow over here has got to be a variable because it's not staying the same? That's not a constant. That S is getting bigger and bigger and bigger. So I can't make up a number for that. If I do, what happens to the sun if I tell you that this distance over here, please understand this because it's really important. If I told you this length over here is like 14 feet, what does that tell you about the sun?
The position of the sun at that point, rather than as a motion.
Yeah. Does it make sense? The sun is now at a certain place in the sky. And if this number stays 14, then does that make sense the sun's not moving anymore? And so that can't be a constant. It has to be a variable. Otherwise, the sun's not moving. And so we're talking about stuff that moves. And I've been telling you since the start of this class that this class is about the mathematics of motion. I'm going to change these little marks to feet since that little prime makes it look like a derivative. And so we reuse that in this section in calculus. So that's got to be feet. That's got to be a variable. Otherwise, the sun can't actually set. And does it also make sense that this length, the distance from the ground, like how tall the sun is above the ground, that would also have to be a variable because the sun is moving. And so would you agree that as h gets smaller, shorter, then s gets bigger? Do you agree with that? Isn't that what we just saw happening a second ago in that Desmos model that I made? So as h gets smaller, s is actually getting bigger. And would you agree my question, just as a curious human being, was really what's my curiosity was really what's s prime? In other words, how's s changing, the speed? And I'm going to say that even a better way today, which is ds dt, not ds dh, but ds dt, because does it make sense? I want the units for speed might be something like, well, let's see, maybe seconds is too fast. Let's say that this is feet per minute. Does it make sense? That's what speed is. It's feet per minute. So what I really am after here for s prime is actually ds dt, because I want to see how s is changing relative to time. And so we've been talking about in this class like dy dx. And so we said, hey, let's take the derivative with respect to x. Well, now we're saying let's take the derivative with respect to time, like a letter that's not even in this problem. And so I was just, like, wow, what's going on with the shadow? Why is the shadow moving so fast? And I didn't understand that. I thought, why does that work? And it turns out calculus is the answer to that question. And you now know enough to understand what I effectively figured out. Now I said related rates. I was effectively curious about this rate. And does it make sense the rate I'm interested in is related to the rate of the sun setting? And so let's give that a rate. Let's say given dh dt is equal to 2 feet per minute. So we're going to give the sun a certain rate to set, or think of the car driving by, whatever, it's traveling a certain speed, and how's my shadow behaving on the ground as that car drives by me or that sun sets. So we're given one rate, and we want to see how our other rate is related to it. Do you see why mathematicians call this section related rates? Okay, let's dive in. And what I want to give you is a pattern as to how to solve all of these kinds of problems. And I'm going to explain this in a way that I think is a lot clearer than it was explained to me. First, if we want to know something about how S is changing and H is changing, does it make sense that we need an equation with H's and S's? We need some equation that's got H's and S's in it. We got to write our own equation. And that's what's going to be hard. And people do find this hard. That's what's going to be hard about this section is you got to write your own equation. In all the previous sections, they just said, hey, here's an equation. They gave it to you. And then they said, take its derivative. Well, in this section, you got to write it for yourself and take its derivative. But fortunately, the derivative taking will be easy. They're not going to be the ridiculous stuff we've just finished with recently. The derivatives will be really easy to take. But we got to come up with some equation that has h's and s's in it. And then the second thing we want to do is, well, get it moving. Because I don't care about s and h. I didn't say, I wonder how high in the sun, I wonder how high in the sky the sun is and how long my shadow would be. I wasn't curious, if you will, about how long h is and how long s is. I was curious about their speeds. Get it moving is sort of code for find the derivative. Take a derivative, because derivatives get things moving. Like, isn't that the key about what was sitting back up here? Those are derivative statements. So I don't want to know about h and s. I want to know about ds dt and dh dt. So that's a derivative. And then just figure stuff out. In my case, I'm really after ds dt. Figure stuff out. Now, this finding equation thing, like we need some equation, every situation is different. But you're really happy when you see right triangles, because right triangles have all kinds of equations. Like they have sine, cosine, and tangent. Notice in my problem, sine, cosine, and tangent are concerned with angles. Like I'd have to get an angle, and I really don't, there's no thetas anywhere here. I'm not interested in the angle. So I don't really want to use a trig equation, although trig does work for right triangles. But there's Pythagorean theorem. Pythagorean theorem is a formula that lives in right triangle land. And so that's interesting to me. Although I don't see any hypotenuses. Anybody see any way to get an equation that involves h's and s's here? Notice there's two right triangles in this picture. There's like the little one made by the tree, and then there's the big one made by the sun. Anybody have any good ideas, any brilliant ideas on how we could get an equation for this?
Area of polygon A plus area of triangle B equals area of triangle C.
That's a pretty good idea. In other words, you have small triangle plus medium sized, I guess you would call that a trapezoid, equals the larger triangle. Maybe there's something I could do with areas that would get that involved. That's a creative idea. Keep going. Anybody have any other ideas?
Could you use Pythagorean theorem, but just have h stay as a constant? So you're just solving for the equation, leaving h and s?
Yeah, like could we use Pythagorean theorem? Well, as an example, if this length up here, like can I call that 17? Is that a constant? Is that length right there from the top of the tree to the shadow on the ground, is that a constant or is that a variable?
Variable.
Variable. So I can't call it 17, but I could call it some letter. I'll just say x. And so does it make sense? I could say 12 squared plus s squared equals x squared now. So yeah, that's totally true. Now, the only thing I don't like about it is notice it's got an x in it. Like I never cared about that. And so is that x going to cause me problems? It would be better if I could get an equation with h's and s's and no other junk. No other junk that I don't want. Let me give you another example of the same thing. Like if I put theta here, since that angle is changing, does it make sense? I could say the tangent of theta equals opposite, which is h, over adjacent, which is this entire length, which would be 16 plus s. Does it make sense? That's an equation with h's and s's in it, except for it's also got theta. And so the question is, do I not like this one because it's got a letter in it that I don't want to know anything about, or is it going to cause me problems?
Well, sometimes you have to find things that don't really matter in the overall thing in order to find what you're actually looking for.
Nice
So
job.
I think this equation would be good because you can actually do something with it that involves your h and s.
You're exactly right. And that that works. Like that is exactly true. Like you might have to find out more things than you want to know. But you may have to do this. In this particular case, there is an easy way to do this that does not involve any extraneous letters. And so I want to introduce this in the simplest way to you I can, but I want to highlight that the key is you got to come up with some equation that relates the information. Now, in your case, the problems are kind of sterile, like somebody gives them to you and then you have to solve them. And so you know, it'll look a little more like what you see up here at the top, which is like, given the speed of the sun is 2 and you want to know how S is changing, you know, that's their givens. And so that's like code for, oh, I need an equation with S's and H's in it. And so the things that you're given will sometimes help you think through what you might choose. But let me show you the easiest answer to this, the easiest choice. So rather than erase those, I'm going to say, for now that we're sort of, let's try sort of step 1 here. These are good, but this is better. What's better? Well, in this case, right triangles, these two triangles are proportionate to each other. Proportions is actually an easier equation in this case. What do I mean? Well, would you agree that you could say in the little triangle, you could say something like, well, I'll say 12 is to S. So I'm saying this length is to this length. So these two triangles share this angle at the bottom. So these two triangles are proportionate. They have the same proportions to them. So if I said 12 is to S in the little triangle, then what would that be in the big triangle? What would I be able to say that's equal to?
H over 16 plus S.
Caesar said that, H over 16 plus S. Do you think Caesar's right, or is he making a mistake? He's right. 16 is just the distance, and that isn't necessarily obvious in this problem, but 16 is just the distance from here to here. That's what I meant 16 to be. If 16 was the distance all the way to the length of the shadow, that wouldn't work because the shadow's moving and the shadow isn't going to be stuck at 16. So he's right. Now, do you see why I'm saying this one's better? Why am I saying it's better?
There's no extra variables.
Yeah, there's no extra variables in it. So this will save me some trouble if that's all I want to know. So mission accomplished. We found an equation for ourselves that relates those letters. And you got to really speak the language of geometry, like to be able to do this. And that'll take some practice. We'll have to talk about that. So awesome. Now we need to, well, get it moving. Why do we need to get it moving? Well, because the person that wrote the problem, or in this case me, was not really curious about just H's and S's, like how long is H and how long is S. They were curious about the speed of these things. So you understand why I need to take a derivative? Because I don't care about the lengths, I care about the speed. That's what I'm interested in. That's why I need to take a derivative, because if I take a derivative, I'm going to get a whole bunch of ds dt's and dh dt's. Well, you should know from the last few lectures that I've been discussing with you that you don't have to take the derivative right now. Like, can't you mess with this a little bit? So let's mess with that a little bit. Like for instance, I don't like fractions. I'm seeing H over 16 plus S and I'm thinking, oh, quotient rule. Ugh, I hate that. So maybe I'll multiply both sides by S. So that would mean the H will get multiplied by S. And on the left side, it will cancel. And then I'm going to multiply both sides by 16 plus S. So the 12 will get multiplied by 16 plus S. And when I multiply it on the right, it will cancel. And I don't even like that multiplication. So maybe I'll multiply it out. Let's see, what is 12 times 16? It is not 12 times 6. It is 192. 192 plus 12S equals HS. Is that better? Should I take the derivative like that? Well, I like that because it has lots of plus signs. It doesn't have quotient rule anymore, so maybe I'll do that. I could also say, well, there's two s's. Maybe I could get the s's on the same side and factor an s out. Like we could keep messing with this. And it may be that we would get to a place that was even easier to take the derivative. I don't know. I'm going to stop here. So now let's get this thing moving, but I'm going to use this one instead. So I'm even going to write the word best here. That's even better. So these are the same equation, but I'm going to use that equation. So let's take its derivative. Let's get it moving. Now, you got to think carefully about what we've been learning lately. Okay, so the derivative of this. What is the derivative of 192? Oh, that's easy. That's 0. Okay, good. What's the derivative of 12 times s?
Wouldn't it be 12 times s prime?
And it's not 12 times s squared. You're confusing that a little bit, Eve, with s squared. In other words, if this was s squared, then the 2 would come down front and you'd have 2s, and then you'd say times the derivative of s. But there's no squared, so that's really just s. Now, what's the derivative of s? Well, the derivative of s is the derivative of s. The 12 just comes along for the ride, so the derivative of s is just the derivative of s. Or you could think product rule. I'm going to erase this, but the derivative of 12 is 0 times s left alone plus 12 left alone times the derivative of s. Oh, that term goes away. You see what I mean when I say the constant just comes along for the ride? Are we okay with that? What about the other side? What are you thinking when you see the other side? What should you be thinking?
The product rule.
Correct, product rule. So again, there's part of me that says, I wonder if I could mess with that equation up there some more so that I could get rid of the product rule. My guess is no, because I find myself thinking, wouldn't I have to divide by s to get rid of it, or divide by h, and then I'm going to have quotient rule, so that's even worse. But yeah, product rule. So the product rule says derivative of h times s left alone plus the h left alone times the derivative of s. Isn't that true?
And h prime is 2 feet per minute.
That's right. And we know some of these. Now, the trick to today is rather than just call this derivative of s with respect to h, like up until today, it was always ds dh or dh ds. Today, we're saying, no, let's take the derivative of these with respect to time, which is a whole different letter. In other words, really what we're thinking of this as is 12 times ds dt. Maybe that helps you. That's s prime. Maybe that just helps you understand what s prime means. It's the change of s relative to time. So s is a distance in feet and time is in minutes. That's a feet per minute statement. That's a speed statement. And maybe that language speaks more clearly than just saying s prime. And then on the other side, I'd have dh dt times s, and then h times ds dt. So I haven't really done anything new. I'm just saying this is probably a better way to think about it. You understand, I now have my second equation, and this is no different than what we've ever done. We said, hey, we had this original equation that graphed a parabola, let's say, in a previous section, and then we said, hey, let's take its derivative, which tells us something about the slope. Except for this time, we're not talking slope, we're talking rate of change. We're talking speed. And so I have really two equations now, both of those equations that are kind of boxed, if you will, clouded. I have these two huge equations, and I don't even know which one to look at, but I think I'll just look at this one. I've got this equation, and I've now got this equation. And these both tell me things that I might want to know. They're both interesting, but now I can actually get its speed. How many unknowns are in that equation up there? Well, I see a ds dt, and that's in there twice. And I see a dh dt and an s and an h. I've got 4 unknowns. This is an equation with 4 unknowns.
Wait, but don't we know dh dt?
Yeah. And so now it just comes down to, if I know 3 of them, then I can always solve for the 4th. And we do know dH/dt. That was given in the problem because we were told the sun was setting at 2 feet per minute. And that's what we're interested in, is how is that rate related to a different rate? Does it make sense we now have an equation that relates those 2 rates? That's what's cool. And it came from an equation that related those 2 lengths, not rates, but lengths. So now let's just figure cool stuff out. So we found an equation, step 1, we got it moving by taking a derivative, step 2, and now let's just go figure stuff out. So we know that dH/dt equals 2. Cool, there's one unknown, so I can throw that in there. Do I know S and H? No, I don't. I don't know S and H, but if you think about it, that makes sense, because didn't we just see a second ago that how fast S was moving depended on where it was? Like if S was back here, wasn't ds/dt, wasn't that speed really slow? Whereas when it was way out here, wasn't it really fast? So doesn't it kind of depend on where you are? So if this is a book problem, there would have to be more givens up here. It'd have to be something like given dH/dt equals 2 and S equals 9, something like that. There'd have to be more givens. But again, what I'm interested in today is to try to help you understand the concept of what we're doing. So I'm going to take a little bit bigger approach. So all we know is
substitute in the earlier equation from the 192 plus 125 equals HS. Can't we substitute in H or S from that into our final equation?
Yeah,
and then only have
we
one
could do
variable
all
to solve
kinds
for?
of substituting. And so we have to know one thing, but based on this equation right here, we don't actually have to know both. Like if I said, I know H is 9, well, then I could solve for S myself. Like I don't have to be told 2 things, but I do have to be told 1 thing. And so, yeah, there's all kinds of things we can do. So let's do this. Let's kind of make a chart and then find more than one answer. Because we just saw a second ago very clearly that the speed of this thing was changing dependent on all kinds of things. And so let's see, where are we going to put the sun? Let's let this be our kind of our second given. So the tree was at 12, and so let's put the sun, I don't know, really high in the sky, like 48 feet, and then let's check again on the speed when the sun drops to, I don't know, 36 feet, and then let's go to 18 feet, and then let's go to 14 feet. Does it make sense the sun can't go below 12? Because then the sun is like shining up in the sky. It's not making a shadow anymore. So I got to keep the sun above 12 feet above the tree to have the shadow hit the ground at all. And so in a sense, in your book problems, one of those will be another one of the givens, and they won't give you 4 questions, they'll just give you 1. And the unfortunate part of that is without being asked all 4 of these questions, you won't really have a sense of how kind of cool this is. You'll just have 1 answer and you'll go, oh, okay, I guess that's the speed. So I'm just going to kind of write us a little note here that says these also have to be given to us. But now that those are given, does it make sense we can actually figure out S ourselves? And this is kind of what Vail was getting at. So we can find S ourselves by looking back at that equation. But notice it's not, well, isn't in the language of what we've been studying lately, isn't this an implicit equation? In other words, it's not solved for H or for S. And that's great, but I would really like it to be solved for S, just so that I can stick 48 in for H and not have to work so hard. So let's resolve that equation. So let's see, I'm going to start from scratch. So if I have 192 plus 12S equals H times S, let's see, I got to get all the H's, I got to get all the S's on the same side. So I'll subtract 12S over to this side, and then I can take S out. I can factor S out of that, leaving H minus 12. And then I can divide by h minus 12. So S is equal to 192 divided by h minus 12. Isn't that a much more useful equation? And as Vale said, could I even plug that in right here and not even have S in this problem anymore if I wanted to? Yeah, you certainly could. But does it make sense that now I've got a really easy way to find S? All I've got to do is go throw 48 into that. So let's just find all those. 192 divided by 48 minus 12, divided by 48 minus 12. Calculator says that's 5.333. I'm just going to round it off. That'll be close enough. 5.3. When I throw 36 into there, what I want you to notice is what's happening to the shadow. Then it's 16, I mean. And then when it's down to 18, now I'm sorry, I typed the wrong thing into that first one. I was looking at my notes here and totally blew that first one, which is -48 minus 12. No, I got the first one right. Let me see. Sorry, I'm such a complete idiot here. 36 minus 12. I just got excited. 36 minus 12. So the second one is 8. So the shadow was 5.3 long. Now it's 8 long. What happens when I put 18 in there? Why is 32 not surprising? I don't mean 32, but why? What's the pattern here?
As h goes lower, S gets bigger because it's going further behind the tree, making the shadow longer.
Yeah, doesn't that make sense? Like as h gets smaller, then isn't this S length out here getting longer? So what do you think is going to happen with this last one? Now the sun is only 2 feet above the tree. What do you think is going to happen with this last one? Well, the shadow is going to be really long. It's 96 feet long now. So as the sun gets lower, as h gets smaller, S actually gets bigger. Would you agree that now I have, so I figured S out myself. Now I have all the ingredients I need to plug in everything in this kind of red equation on the top, except for the one thing that I want to know. I want to know what ds dt is. Now I know that dh dt is 2. And in this first problem, don't I know that S, I think I'll write this down below instead of messing up my example. So 12 ds dt equals dh dt times S plus h times ds dt. Trying to give you time to maybe even get ahead of me here. So let's see, I was told that dh dt was 2, and I now know in this first example that when h is 48, when the sun is 48 in the sky, that the shadow length is only 5.3. And so isn't there, since I know 3 unknowns, isn't there only one thing left to solve for, ds dt? But again, notice ds dt happens to be in this equation twice. And so I'm thinking, gosh, to solve for that, it just seems like a pain. And I think I'm going to do something even better. Like before I even plug those numbers in, and what I'm getting at here is, do you speak the language of algebra? Just like I did over here, when I resolve this to spit S out, I'm going to resolve this top one so it'll spit ds dt out. So rather than use that, let's see, how do I solve for ds dt? Well, I could take this ds dt that's on this side, and I could bring the one over from the other side. So now all the ds dt's are on the same side, and the non-ds dt's are on the other side. And then couldn't I factor that out? Let me see if I can just squeeze all this onto the same page. Couldn't I factor all of that out? And then if I did that, then I'd be dividing. So I'd get ds dt. If I factored that out, it'd be times 12 minus h. And then I just divide it to the other side. So since I'm out of space, I'm going to do that in one step instead of two. So wouldn't that make ds dt equal to dh dt times s, all divided by 12 minus h? Isn't this going to save me some time? So I'm going to plug my stuff into that instead, because I think that's a nicer equation. So it's going to make my life a little easier. Remember, I got to do this 4 times. And so now it's all solved for this just once. And so now I'm going to put in h is 48 and s is 5.3 and dh dt is kind of permanently 2. And so, okay, I might get my calculator out. I say 2 times 5.3 divided by 12 minus 48. And I got negative 0.29. For my speed of my shadow. Negative, about negative 0.29 or negative 0.3. Wait, negative?
Shouldn't DHDT be negative because the sun is going down?
Yeah. Now I did this on
Okay.
accident in my 8 o'clock class, but if DHDT is positive, does it make sense? That's implying the sun's going up in the sky, not down. Does that make sense? So that's why it's negative. If the sun was going up, wouldn't that cause the shadow to move left, and then S would be getting smaller? So DSDT would be negative. And so, yeah, in a sense, I hope that isn't tricky on an assignment question, but really this should be a negative 2 because H is getting smaller. So that's worth fixing. If I do that, then nothing changes except for the answer. Now, why is that not surprising? Remember what that is, that what we just got there is feet per minute. What happened to the shadow? What happened to the shadow here when the sun was way in the sky, really high up there, and it was setting? How was that point growing?
It's growing very small because as the sun goes down, it's not hitting the tree yet a lot. And so it's not really behind it. So your shadow won't be big, will be very, very small because it's way up there and it's just pointing down at the tree, practically making the shadow non-existent.
That's exactly right. So we saw the shadow was not moving very quickly when the sun was high in the sky. That kind of makes sense. But what happens when it's 36 and 8? Well, notice the 2 doesn't change. But now this is a 36 and an 8. So I'm going to go back in here, put 36 and 8 in. Now what happens? I get negative 16 on the top divided by negative 24 on the bottom. And now I get 0.7 feet per minute. Notice it's still not moving very fast, but it's moving faster because the sun's getting lower in the sky. Isn't this the pattern we just saw a minute ago when I showed you that animation? What about when we're clear down to where it's now getting close? Now we're down to 18 feet. And in that case, the shadow length was 32 feet. Now we're starting to get some serious numbers. So on the top, negative 2 times 32 is negative 64. Divided by 12 minus 18 is 6. 64 divided by 6 is actually 10.7. Notice the shadow is really starting to move out now. It's moving way faster. Remember, the sun is setting at a constant rate the whole time, and yet the rate that's related to it is going quite a bit faster. And this last one's going to be going really fast.
I have a question real quick.
Please.
When you did your finding the derivative for S with respect to time for the first H, when H is 48 and S is 5.3, did you get something like 0.35 or something that would round to 3.5?
Let's see. I used 5.3 and I got 0.29 for that. And I used 5.3, not 5.3333. Okay. S is really 5.3333, and so it's just a question of rounding, I think.
Because I'm noticing we're kind of doubling increase, if that makes sense, like if it was 0.35
Right,
to
I see what you're saying.
0.7.
Yeah, is it doubling? And that very well may be the case. In other words, if you look over here and there's a pattern, like if I looked at 48 and then 36 and then 12 less at 24 and then 12 less at 12. If I decrease these heights kind of at a constant, like at the same exact place, then maybe these speeds would behave similarly.
Yeah,
So you're exactly right. That very well could be the case. This last one is actually 9. It's unfortunate. It's coincidentally exactly the same as S, but it's 96 feet per minute. So, I mean, you see, like it's calculus. That's the answer to my question. My question is, wow, why is the shadow outrunning me as I walk down the beach right here? What's going on? And it took me a long time, just as a curious human being, when I had time to think about it, to kind of draw pictures of this. And it actually took calculus to answer my question. I didn't know it was a calculus problem. I just thought it was like, wow, why is the shadow moving so fast? I didn't know even what it would take to answer it. I figured it was a math problem. I thought maybe I'll have to know something about astronomy or how the sun works. I wasn't sure all that I would have to know, but you now understand this. Like this is the math as to why the shadow is moving so fast out there. You can see it happening right here. Again, what you're going to be asked on a test on your homework assignment is just one. Like I give you 4 different answers here so that you can see how dynamic and how cool it is, but you're just going to be asked one of them. So your problem, they probably give you a figure, but they'll do something like, there's like the sun is a light pole. And I think this is one of your questions, if I remember right. The sun is a light pole, so it's not moving, but you are the tree and you are moving, like you're walking in this direction. And so it'll ask based on how fast you're walking, how fast is the shadow growing? That's a classic question as an example. And they'll just give you one scenario. I did 4, but they'll just say, given DHDT is -2 feet per minute, or maybe they won't tell you it's negative and you got to figure it out yourself. If something's getting bigger, it's positive. If it's getting smaller, then it's negative. And then they'll give you one other piece of information like, oh yeah, what is that? What is the speed of the shadow when the height is at 36? And so maybe they'll just be giving you like this question right here. When the sun is 36 feet in the air, then how fast is the shadow moving? And you'll say 0.7, and you won't have any context of like, is that fast? Is that slow? Or why is that so slow? But this is cool. I mean, in a crazy kind of a way. Math is the language of the universe in the sense that if you want to understand stuff in the real world that's moving, if you look out the window, I said this before, if you look out the window and you see something not moving, then you don't need calculus. But if it is moving, then you're going to need calculus to understand what the heck is going on. It's just really cool. Let's look at another similar example. We're done with that one. How to avoid a speeding ticket. I'm going to show you how to get out of a ticket. So here you are, ripping down the road at 90 miles per hour. So you deserve a ticket. And as cops are wont to do, let's say the cop is sitting right here behind a overpass or a bunch of bushes or something like that, and he's looking at speed. He's checking speed with his radar gun. And you come out from behind the bushes right here. You're here. Notice that's at 90 degrees right now. And so you're at the green dot right now. And the cop has the radar gun pointed at you. And I want you to think about this carefully. The cop has the gun pointed right at you, right when you come from behind the bush, and he pulls the trigger on the speed gun. What does the gun read? I don't necessarily think you would know the answer to this.
0, right?
Vale says 0. Do you think he's right? Like your speed's 90. Why would it read 0? Vale's right.
Because it works by measuring how long the response time is from how long it takes to go to the object and come back. So you need 0 for the starting measurement, and then as you move, it'll increase the speed it shows.
Yeah, what the gun is measuring is how fast you're moving toward the cop or away from the cop. Are you moving toward or away from the cop here? Are you moving in this direction, like toward the cop, or this direction away from the cop? No. He's going to read 0 if he, but you're not going 0, you're going 90. So, what's the deal with that? What if you're out here? Again, what does the cop read? The cop reads that speed right there. Is that length right there getting bigger? Yes, it is. This is a variable. This is like G for gun. That's getting bigger. The cop will now read a speed. What speed will he read? Will it be 90? The answer is no. Let's say this was a slightly different situation and you're down here and you're going 90 miles an hour and the cop is right here hiding behind the bushes. And right when you go by, the cop jumps out onto the road and aims the gun at you and shoots. Now you're going 90 on his gun. You understand that? Because he's going directly away from you. But if he's not going directly away from you, then his speed he reads is never going to be what's on that gun. And this is a part of cop school. I've seen the paperwork on this because I don't remember where I ran across this question, but I saw the books, the manuals where they explain to cops where do you sit in order to get someone's speed. And you got to sit where they're coming towards you or away from you. Like if this is the road, the cop might sit right here as you're coming toward them on the road, as you're ripping along this direction, because they're basically going right at the cop. They're going to get in the road, right? They're going to be next to the road. The cop never goes out here because they won't see the speed that you're actually going. They got to be close. You got to be going toward them or going away from them in order for this to work. So this is a related rage question. Let's figure this out. So I've given you some context to the problem. Now let's put you right here, out there. And what I want you to understand again is, just like last time, there is a right triangle here. We like right triangles because there's so many formulas associated with them. Now, triangles have 3 angles and 3 sides. So 3 lengths and 3 angles. Which ones are variables and which ones are constants? If you're moving, now if you stop, they're all constants, right? But we're not stopped. We're moving down the road at 90 miles an hour. So the 3 lengths, is this length down here constant or a variable?
It's a variable.
It's a variable. So let's call it C for car. That's car. That's a variable. It's changing. It's getting longer, right? What about this length up here?
It's also a variable.
It's getting longer. It's also a variable. Let's call it G for gun. What about this length right here?
That one's constant.
That's actually constant. Like how far is the cop sitting from the road? Does it matter? Does it matter where you are? No, doesn't make any difference at all. So that's actually a constant. So let's call that 50 feet. What about the angles in this problem? Do you agree that the angle that I drew in here, 90 degrees, that's also constant?
Yes.
Yeah, it's constant, isn't it? But wouldn't these other 2 angles be variables? What's happening to that angle out there as you keep driving? What's that angle doing? Is it getting bigger or is it getting smaller?
Smaller.
That's getting smaller, isn't it? And then this angle's getting wider up here. Does that make sense? So I could put variables in for all those things. I might erase these, but for instance, this could be theta. A lot of times use Greek letters for the angles. And so those are the variables, those are the constants. We have 2 constants and we have 4 variables. 2 are angles, 2 are lengths. And so again, it's just a question of what are you interested in here? Well, in this problem, we don't really care about angles. What we're really curious about in this problem is, well, what we're curious about is dg dt. this is the one we want to find. Do you understand why that's the case? That's because that's what the cop sees. And that's what the cop pulls you over for, is DGDT. How fast are you going?
Specifically, don't we want DGDT over 90?
Say that again. DGDT what?
Specifically, don't we want DGDT and its relation to 90?
Exactly. It's DGT related to 90.
Yeah.
Now, do you agree that because I named this side C right here, that 90 miles an hour is code for DCDT? Like that's how how C is changing, isn't it? Isn't the length C growing? It's positive by 90 miles per hour. So in a sense, this problem is given the car is driving 90 miles an hour, find DGDT. These two rates are related. Find DGDT, and then I would have to give you a snapshot in time, just like we did last time. Because it depends where you are. We already said earlier, down here, the cop actually, the radar gun's gonna say you're going really slow. But out here, it's actually gonna say you're going a lot closer to 90 miles an hour. So it depends where you are. So there would have to be a second given to this problem. And we're gonna go on and answer more questions, but let's list these two givens just so that it looks a little bit more like your book assignment. Given, let's say 1, C equals 12 feet, and 2, that given the speed. So that looks a little bit more like a book problem now. Now we're going to go on and answer other C's besides 12 feet. All right. To survive this, we've got 3 things we've got to do. We got to come up with some equation, in this case, an equation that has C's and G's. And as we said before, it could have other things in it. Like for instance, if I put theta in here, couldn't I say the cosine of theta is adjacent over hypotenuse? But that's got a theta in it, and I'd rather not have theta in it. So there's better equations than that. Can anybody come up with an equation that's got C's and G's and doesn't have any of the other letters in it?
G equals root 50 squared plus C squared.
Pythagorean theorem. Pythagorean theorem says that C squared plus 50 squared has to be equal to G squared. And Vail solved it for G or C. I can't remember which one he just said, but it's like, would you agree that's the best equation here because it's only got C's and G's in it? And so this is going to do it. I found an equation that relates G and C and no other letters. I don't mind the 50 being in it because it's just a number. I do mind other things being in it if they're letters. So that's interesting. Great, mission accomplished. And again, maybe I should solve this for something else. Maybe I should resolve it. I certainly can at least multiply 50 squared out to 2,500. So I'm going to kind of note that. There's my, well, I might even say this is my, in the language of the other classes I teach, that's my static equation. This is the equation of things not moving. So for that reason, why do I not want to go in and just plug 12 in right now? Wasn't 12 feet a given? Why do I not want to plug 12 in right now? C is 12. Why do I not want to do that?
Is it because you don't have the G isolated by itself?
It's even worse than that.
Because you're trying to solve for the derivative.
I need the derivative. And would you agree if C is 12, that contradicts the speed? Like if C is stuck at 12, then you're not moving. You see what I'm saying? So 12 represents the snapshot in time that I'm interested in, because that's when the cop pulled the trigger when you were at 12 feet. But you don't want to plug that in before you take a derivative. And so many of you are kind of getting onto that. So I don't want to plug that in too soon. And that's one of the things that makes these questions really hard. You want to find an equation, but the second step to this is get this thing moving. That's not the equation we want to plug stuff into. We want to plug it in where the derivatives are involved. We don't want to plug it in the static equation. We want to plug it in the dynamic equation. Okay, well, let's get it moving. What's the derivative? I'm gonna pick on somebody. It's okay if you're wrong. Say I don't know. Jerry, what's the derivative of c squared? Jerry, are you in the building? How about Drake? You can say you don't know. You're there, right? You're there. All I see is a black screen.
He said his mic doesn't work in chat.
Mic's not working. Oh, you sent a chat. Sounds good. What about Jaleesa?
My guess is 2c times c prime.
I like that she said my guess. Isn't that exactly where you should be in this class right now? You should not be perfect at this. So she has an educated guess. She's exactly right. The derivative of junk squared is 2 times the junk times the derivative of the junk. Except for we're writing C prime in a much more informative way in this section.
I was about to say, wouldn't it be 90 miles per hour over your unit of time? So
Yeah.
90 miles per an hour.
Yeah, and don't we know dc dt is 90 miles an hour? So like I can put 90 in for that. We'll do that in a second, but let's finish taking the derivative. So then let's see, plus 2,500. Well, the derivative of 2,500 is nothing. And then the derivative of g squared would be 2 times g dg dt. Does it make sense that I've got it moving now? Like this is what I want to plug stuff into. Why? Because I was interested in speed. I'm not interested in distances. I'm interested in speeds. This is what, in the language of the 2 engineering equations, engineering classes I teach, this is the dynamic equation. Static means it isn't changing. Dynamic means it is. This is the one I want to plug stuff into because I'm interested in speed. Now I'm ready to rip. So again, what we have here is an equation that has 4 unknowns in it. It's got a c and a dc dt, a g and a dg dt. In the language of algebra, it's got 4 unknowns. And so if you give me 3 in the context of a boring book problem, if you give me 3 of them, I'll be able to calculate the 4th. And of course, the one I'm trying to calculate, the one we are curious about from the start, and the one that you'd naturally be curious about is dg dt. Like I want to know how fast the cop pulls the trigger when I'm at 12 feet. When C is 12 feet, then what speed is the cop going to read? So we got everything we need to, well, move to kind of the 3rd step, which is just figure stuff out. I got everything I need. Let's go do that. So here's the question. This question has one slight curveball into it. Let's see, what do I know? Well, I was told that I was interested in the snapshot in time when C was 12 feet. This is where I want to plug 12 into. And we were told that dc dt, the speed the person was traveling was 90 miles per hour. Anybody concerned about that? Let's see. Wow.
Don't we have to convert it to feet?
Yeah, do we need that to be feet somehow? That's actually an interesting question. My gut reaction to that was, yeah, we got to convert this. But does it make sense if we didn't convert it? The units on the left side would be feet miles per hour, whatever the heck that means. And if we came over here and did the same thing, if this was in feet and this was in miles per hour, I guess, I never even thought about this, but I guess we don't have to convert this. I was thinking we did. I did it in my last class. I actually don't think we have to convert this because the units on both sides will be feet miles per hour. So that's not. But in order to solve for miles per hour, don't we have to know what G is? How are we going to know what G is? Like we don't, that's
Put
one we
G
don't
on
need.
your first equation.
Yeah, go back to your static equation. So we do need this equation. We do need to stick 12 into this to get G. So if I put 12 in there, let's see, what does G give me? Square root of 12 squared plus 2,500 is 1.4 approximately. So I put 12 into this, I get out approximately 51.4 feet. And so I can plug that in to this equation. Notice I don't really need the 2's. I could have canceled those out. So I'm just going to leave the 2 out. So if I say 12 times 90, this is a really quick, easy equation to solve. If I say 12 times 90 equals 51 times GDT, all I got to do is divide 12 times 90 by 51.4. And I get 21.
I have a question.
Please.
What about the units in this? Wouldn't that affect it? Because I feel like just doing 12 feet times 90 miles per hour is confusing.
Yeah, I agree. And I will say to you that I've taught this class for like 20 years, and I've converted it every time. And right now is the first time I ever looked at that. I've gotten a lot better at units since I started teaching engineering. And so because the units on the left are feet miles per hour, even though it's kind of a weird unit, and the right, the units are feet miles per hour, we don't need to convert this. If you do convert it, fine, it still works great.
Okay.
And I'm worried that me saying this to you is going to screw you up with problems, because there are times when you might need to convert it, but no, I actually don't think we need to. But again, let's answer some more questions. Like when C is 12 feet, then what is dg dt? It was 21 miles per hour. Again, does that actually make sense? Look back at the picture. So the cop is 50 feet away, so you'd be like right here. So even though you're going 90, you're still pretty close to the cop. Does that make sense? And so he's not going to read anywhere near close to your speed. That's what they teach in cop school, is don't pull the trigger right then. It doesn't make any sense to pull the trigger right then. But what if we, let's do some other questions. What if we went out a little further? Like what if we were out at 60 feet? Let's redo this with 60 feet. Well, that'd be 60 times 90 divided by 51.4. When I did that, I got maybe this does matter, because I just got, oh, it's not 51.4. Yeah, if I'll redo this in another color. If I stick in 60 for C, then G is not 51.4. So I actually got to refigure that out. 60 squared plus 2,500 raised to the 0.5 power, 78.1. So in a sense, I need to have that written down here too. So I need a spot for G. So it was 51.4, now it's 78.1. And then we get GDT, which in the first case was 21. And this time it's 60 times 90. But then I'm dividing by 78.1. There we go. And I got 69 miles per hour. Are you getting a ticket?
Well, what's the speed limit?
Let's say we're on the freeway. It's a good question. We're on the freeway and it's 65. Would you get a ticket? The answer is probably no. They don't really pull you over unless you get into 70. So you probably wouldn't get a ticket for this. But again, notice you're traveling the same speed the whole time. So the cop pulls the trigger here when you're at 60, and they're reading closer to your actual speed. Well, let's go out a little bit further. Let's go one more distance out. Let's say you're kind of quite a ways out there, like say 200 feet now. Well, again, I got to figure out. So I've got to go 200 squared plus 2,500 square root that. If I do that, I get G is 206. 206.2 approximately. Let's just draw a quick picture. Does that make sense? Let's see, 50 feet here, 200 feet here, so like 4 times as long. Yeah, that wouldn't it make sense if this was 200 that this wouldn't be that much longer? That kind of makes sense, doesn't it? So again, just to stir your brain a little bit. So then if I stick 200 in for this, 90 is a constant because you're going a constant speed, and I stick 206.2 in for G, so I have 200 times 90, and then I divide that by 206.2. Notice your speed is 87.3. Do you see what's happening? It's approaching a limit. In other words, now you're far enough away that he's only reading the speed and he's only off by like 3 miles an hour of your actual speed. Now you're going to get a ticket. So again, the book's only going to ask one question, but it kind of takes away the beauty of what this is accomplishing. It depends where you are. Just like a second ago, how fast is the shadow moving? Well, it depends where the shadow is, or it depends where the sun is. How fast are you going according to the cop? Well, it depends on when he pulls the trigger. If you're way out there, he's basically going to get your exact speed. In cop school, this is what I saw from this book. In cop school, they say this angle has to be less than 10 degrees. In other words, don't even bother kind of aiming at them unless the direction you're aiming and the direction the car is traveling are within about 10 degrees of each other. It's not like to get out a protractor on the ground. But don't bother, basically, is what they teach in cop school. Now, they're not showing them calculus, they're not showing them trigonometry, all that junk. It's you guys. You guys are the engineers. You're the future engineers that make these manuals that tell cops how to use their gun and so forth. But you got to learn how to think to make stuff like this up. You got to be able to reason a little bit. And if I went even further out, I'm not going to do this one. I'm going to erase this. But if I went up to like 500 feet, does it make sense? This might be like 89.9 miles per hour, because now you're way out there, and so you're pretty much lined up with the cop now. You're so far out there now that angle, that sliver of an angle right there is really tiny. Let's see, what would this angle be? You know trigonometry. What is that angle right there if this is 90 degrees? Well, that'd be cosine. So if I go second cosine of 200 divided by 206.2, I get 0.24 radians when I multiply that by 180 divided by pi. That's 14 degrees. This angle right here would be 14 degrees. And so in cop school, they'd say, don't do that. It's not far enough out. You can see why, because notice this angle, this is pretty close now. Your speed's 90, but the gun reads 87.3. So if they tell the cops, hey, keep it less than 10, then it'll be really accurate. I see why they said that. What I'd like you to see is that these two examples that I had time to do today to help you understand the intuition of this are the same exact example. It's just find an equation, take a derivative, plug stuff in. But it's no joke to find an equation. Like that's not always easy to do. And I made it easy today because both problems were right triangles. But what if they weren't right triangles? Do you know law of sines and law of cosines? You can actually make up all kinds of cool stuff. I'll just say one other quick thing kind of going out the door. You've played games, right, that have kind of an hourglass kind of shape to them. So you got all the sand up in the top and you got so many minutes to like come up with a number of words that are synonyms for wallaby or whatever. And the sand is going out. What have you noticed about how fast that sand goes out? Does it just go down at the same speed the whole time?
No, it slows down as time goes.
Yeah, what happens is this distance right here, let's call this distance S for sand or something, is at the same speed as when the sand is like right there. And this is what we're talking about. is, can you figure out why that is? You may know that it's not the same. My recollection is that back here, it actually isn't moving very fast. It kind of seems like
Yeah.
it's really moving.
Yeah, I remember that now.
And then when you get down here, it's in a sense, this is what vectors are for in physics, but up here, the speed is really tiny. It's a small arrow. Whereas down here, it just goes whoop, and it's like gone. And the last couple seconds, like the depth is changing super quickly. And so, again, it's calculus that would allow you to answer that question. And so what I want to do tomorrow is spend less time helping you understand the concept behind this and try to get to more examples and just try to help you get the homework assignment done. Because I want to split the difference a little bit in that regard. So let me just give you a precursor, a pre-example. Maybe you've seen this. This is a conveyor belt. Sand is on here and it falls off on the ground. So you start this is what happens at a rock crushing plant. And so sand falls down here and lands on the ground. What happens as that just keeps going? What forms underneath that? What?
A mound, a cone shape.
That's exactly right. Kind of a cone-shaped mound forms. So you end up with this. Whoa, that's drunken. You end up with this kind of cone-shaped mound of sand. So would you agree that the sand is coming off the conveyor belt at a constant rate? The conveyor belt's just moving. And so maybe a certain amount of sand is falling off. But notice the pile's also growing. And so you might wonder, like, based on the speed at which this sand is coming off, I wonder how fast the height of the pile is growing. And does it grow the same? Does the height grow at the same all the time? Does it grow the same speed when it's really tiny or down here as it does when it's really large? Like, these are the kinds of things that this section is about, is related rates. How does the rate of one thing affect the rate of something else? And so I just want to get to a bunch more examples tomorrow about things of that nature. So writing your own equations is no joke. Like, you got to have a pretty broad understanding of math to do that. I gave you, if I remember right, a formula sheet that has a bunch of geometry equations in that. We're probably going to need some of those tomorrow. And so anyway, where are we? Tomorrow we're going to practice this a little bit more. Ultimately, what I'd like you to get down in your mind is kind of what I'm describing is kind of this sort of 3 things that you got to do. This is how all these problems are the same. Those 3 steps. I hate to use the word steps, but the process is the same for every type of problem. And then Monday we're reviewing for a test, and then Tuesday we're taking a test over the last half of chapter 3. So tomorrow, by the end of the day, you owe me your take-home quiz, which I can grade and get back to you in time for you to learn from your mistakes. And then you also owe me the project about the tangent line sliding along the curve. So we're coming up to some stuff being due. All right, we're done on time. That never happens. Stay after if you want to ask me other questions, either about what we did today or about that quiz that's due and about your project. And otherwise, I'll see you tomorrow.
If nobody has any questions about class, I have a question. It doesn't exactly pertain to class, but I'm dying to kind of know the answer.
Good for you.
So we talked about previously for the project polar graphs, and I decided in the end against doing a polar graph. But how do you find the derivative of a polar graph? Because it's not the same as finding the